touch screen. This is a simplified model of the touch screen where the capacitance of the human body and the finger is replaced by the grounded touch area. There are 4 electrodes connected to the corners of the conducting sheet, and the current for these electrodes through these corners depends on the grounded touch area position. I am going to simulate this device using two-dimensional DC conduction model of QuickField. Okay, let's start QuickField now. In QuickField, I create a new problem, touch screen. Next. Problem type is DC conduction. Model class is plane parallel. Length units are millimeters, and the screen thickness is 0.1 millimeter. Finish. To construct the geometry model, I will insert a rectangle with the dimensions 200 by 100 millimeters. And I will insert a circle that will represent the touch point with the diameter of 10 millimeters. Insert. Close, zoom to fit. And I'm going to add some edge, so I will switch to insert mode and draw these lines here. Then I will switch to select objects mode and remove these corners. So the geometry model is ready. To distinguish one geometric object from another, I should assign labels, and through labels I can provide physical properties to the objects. Click to select and type in the label name. This is screen, and I have 4 electrodes, A, B, C, and D. And this is the touch area with 0 electric potential, so I will assign label to the boundary of this area. 0. Now let's provide physical properties for these labels. Double-click the label name in the tree. Electrical conductivity of the touchscreen is 100 Siemens per meter. Electrodes have the same electric potential of 1 volt. And the touch area has 0 electric potential. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Here you can see the color map of the current density distribution, and to measure the total current in the electrode, I should use the contour tool to build the integration contour. Click the edge to select it, follow to the integrals, and current through the surface. Let's put this value in the table. Copy and paste it here. This is the conductor A. Contour clear. Click to select another conductor. You see the value is negative. That's because the contour is directed differently. The contour is the line that has a direction. If you change the direction of the contour, the sign of the integral will change as well. I'm going to change the direction, so I will operate with the positive currents. And to find the actual direction of the currents, you can switch on the vector plots. So you see, indeed, the currents flows from the corner electrodes towards the grounded area. Again, copy this value. This is for conductor B. contour clear. This is conductor C. Contour clear. This is conductor D. Let's change the number format to be the same. Format general. You see, the current through electrodes is the same because the finger is placed in a central position. But what will happen if we move the finger? Let's do it and run the analysis. Open the geometry model, select the finger and move it to some other position. Build the finite element mesh, solve the problem again, open the results. Now you see the color density color plot is not symmetrical anymore. I will adjust the field picture and switch on the vectors plot. Here the current density is much higher, and in these corners the current is low. Let's find the exact values. Again, I will use the contour tool, click to select the edge, copy, paste it here, contour clear, contour change direction, copy, paste it here, contour clear, copy, paste it here, and last electrode, paste it here. A, B, C, D. Again, let's adjust the number format. So this way you can calculate the currents through electrodes for any position of the touch area. But there is a way to automate the calculations. You can use the label mover tool. Label mover could move labeled objects and calculate integrals for labeled objects. First, I should select the base problem. It's already selected. Next, I should specify the values to measure. Add values. I would like to measure the current for the electrode A, for the electrode B, for the electrode C, and for electrode D. Okay, and I'm going to change the position of the touch area. Record steps. I would like to move the touch area to the right by 5 millimeters. Add step. Close. You see the new problem is created where the touch area is moved to the right by 5 millimeters. And I'm going to repeat this step, well, while possible, till this area hits the screen boundary. Okay. Now that's all. I have the base problem, I have specified the values to measure, and I have specified the steps to perform. Let's get the results. A series of problems is generated. In each problem, the touch area is placed in new position. Then these problems will be simulated, and the results will be stored here in the table. The results are currents through A, B, C, and D electrodes. On computers with multi-core processors, label mover can open and start simulating several problems simultaneously. One problem per each core. It took about 10 minutes to simulate all 31 problems. And here you can see the results. Now let's make some plots of the results. This is the current through the A electrode as a function of the finger position from left to the right. And for the B, it is, oh, I should have changed the contour direction. So again, it should be like this. Okay, for the C, this is the C electrode. And for the D, the results you can copy, select all, copy and paste in the table. A, B, C, D. And these results are calculated only for the one row. What if I need to calculate the results for another row? That's easy. Open the base problem 0. Change the initial position of the touch area. Save problem files, and you can again use the label mover to generate a series of problems and calculate the currents through electrodes. If you search for the touch screen on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results can be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.